Good morning and welcome to the video course on advanced hydrology. In the last class, we looked at a few examples of unconfined flow and confined flow, or rather one dimensional flow in a confined aquifer and unconfined aquifer. And for the case of unconfined aquifer, we had the recharge. All right. So, we looked at the general case of this unconfined flow with recharge. Today, we would like to get started with the last topic in this course, which is on the well hydraulics. All right, because all of you know that majority of our country depends upon the groundwater, and how do we extract the groundwater is by digging the pumping wells and pumping out the water from it. So, when we pump out the water or the groundwater through a pumping well, what happens in a aquifer, all right, or what kind of flow takes place and how we can find out the aquifer parameters or how we can determine the yield, etc. So, understanding this well hydraulics is very important. Okay. So, this is what we will start with today. So, we will start with well hydraulics. Okay. So, what we will do is let us consider that water is being pumped out from an unconfined aquifer. Okay. And the aquifer is homogeneous and isotropic. We are going to assume these types of conditions almost always. Okay. So, first we are going to look at the case of the unconfined aquifer, the well hydraulics, how the radial flow will be taking place towards a pumping well. Okay. We will derive the equation for the discharge which can be pumped out from the unconfined aquifer. All right. However, before we go to that, it is important to understand certain terminology, the definitions and some basic concepts about the well hydraulics. Okay. So, we will get started with that. Okay. So, we will look at the schematic here first, like we have been doing. This is your impervious boundary, which is at the bottom of the aquifer. Okay. And then on the top we have the ground level. Okay. And then let us say we have we are pumping water through this well. So, this is your well. Okay. And let us say that the well has a diameter of 2 RW. So, RW is essentially the radius at the well, that is what we are saying. Okay. Let us say originally the groundwater table is like this. All right. So, this is your original groundwater table, and once you start pumping the water, you are going to have drop in the water table like this. Okay. Let us say the total height is h originally. Okay. And then let us assume that we have some observation wells which are dug into the unconfined aquifer at certain distances, right. These are what is called the observation wells. These two. So, we are not pumping water, but just looking at the water table, or we are just measuring where the water is, the depth of that. Okay. This curve is what is called the drawdown curve. Okay, the lowering of the water table, all right, and this whole area we are looking at is called the cone of depression. We are going to look at all these things in a minute. Okay. And then we are going to measure everything from the center of the well. Okay. So, let us say this is capital R, and we will define all these things, and at any distance r from the well, let us say this distance is S, okay, and the height of the groundwater table is, let us say, H from the bottom of the aquifer, okay, and this is at some distance r, all right. So, it will be a function of r, and r is this distance. Okay. This is your unconfined aquifer, okay, and it has certain conductivity, let us say K. Okay. All right. So, what we are saying here is that your S is actually called the drawdown. Okay. Drawdown is what? It is the lowering of the water table as a result of the pumping, all right. Originally it was horizontal, and then after some time the water table has gone down in the aquifer. Okay. This we are saying will be function of the radial distance. As you go away from the pumping well, this drawdown will reduce. Okay. Similarly, H is we are going to define as the height of the groundwater table, all right, at a distance r. Okay. So, this H is function of r. Okay. Then we have defined a capital H, which is the height of your groundwater table from the impervious bed, of course, all these things. Okay. Originally, that is before the pumping, all right, or also we can say during pumping at r is equal to capital R. Okay. Now, what we will do is let us look at some of the definitions. What do we mean by drawdown? Okay. It is essentially the drop in the groundwater table from original static or stationary rather groundwater table when water is pumped out. Okay. So, what is the drawdown? Drawdown is basically you have the groundwater table, originally it is horizontal, all right. So, you have dug a pumping well, you are pumping the water out. As a result of that, water is coming from the storage. So, what will happen to that groundwater table? It will reduce, all right. So, this reduction in the groundwater table, all right, is basically will be different as a you go away from the radial distance from the or the center of the pumping well. Okay. So, this value of this S is the distance between the original groundwater table and the current water table. Okay. That distance is called the drawdown or the lowering of the water table. The next thing is what is called the cone of depression. Okay. So, if we look at the in the 3 dimension, it will look like a cone, all right. So, what we are saying is that the shape of the drawdown curve your drawdown curve in 3 dimensions, all right, is called the cone of depression as water is pumped out, as a result of water being pumped out of the aquifer. Okay. So, what is the cone of depression? All right, you have the original groundwater table, all right, it is getting lower. So, if you are looking from the side, or from any angle, you will see that the groundwater table is going down. But if you look from the top or in a 3-dimensional picture, then you will have a cone forming, all right. So, it will be a conical shape of your drawdown curve, which is called the cone of depression, all right. The whole groundwater table is getting depressed and it is forming a cone. Okay. The next concept is we call what is called the area of influence. Okay. As the name suggests, it is the areal extent of the cone of depression. So, it is nothing but the areal extent of the cone of depression. Okay. And it is easy to see what will be the drawdown at the area of influence or beyond the area of influence. Well, drawdown will be 0, okay, because as you go away from the well, the drawdown is decreasing, all right, and the area of influence, it will meet the original groundwater table. So, the drawdown is 0 at the area of influence and the beyond. So, you have drawdown is equal to 0. So, if you want to find out the area of influence, what you do is on your map you find out the area where the drawdown becomes 0, all right, and then you can delineate the or find out the area of the influence. Okay. All right. So, here let me say on this is your pumping well, okay, and you are pumping certain amount of water Q out of this, and we are interested in finding that out. Okay. And then this area of influence will be this whole thing, area of influence. Okay. So, if you look at this aquifer from the top, all right, a cross section, you will see a circular area, all right, that is called the area of influence, all right. And then if you take the radius of that, that is called radius of influence. And this we are going to say is capital R. Okay. So, the next thing is radius of influence. Okay. What is that? It is essentially the radius corresponding to the area of influence. Okay. All right. So, these are the basic terms which actually we are going to be using when we derive the expressions or whenever we talk about pumping from a unconfined aquifer or even for the confined aquifer. Okay. Now, what we will do is we will look at what actually goes on inside a well or a aquifer, all right, as we start to pump the water out. Okay. So, just try to think what will happen in the aquifer, all right, it is more of a common sense. Okay. As we do that, what kind of an activity will take place and what will be the changes in many of these terms which we have just defined. For example, the cone of depression, what will happen to that? Okay. What will happen to the drawdown? What will happen to the height of the groundwater table? All right. Ultimately, our objective is to understand the behavior of all these characteristics in a aquifer. Okay. So, let us start looking at what happens as the water is pumped out. Okay. So, we are going to look at a few things, all right. First of all, as you pump the water out from a unconfined aquifer here. So, initially the flow will be steady or unsteady. As you pump the water out, all right, you just started pumping water out at certain rate which is constant, let us say. Okay. So, the drawdowns will be changing, right, the height of groundwater will be changing, groundwater table will be changing, all right, the area of your cone of depression and all of those things will be changing, right. However, this process will be steady or unsteady initially. Okay. Obviously, initially things will be unsteady, all right, because they are starting from 0, all right, and slowly things are changing or improving or increasing or reducing, all right, depending upon what you are looking at. So, initially the flow will be unsteady. Okay. That is to say, your H will be function of what? Both R and T, and also your S will be function of both R and T. Okay. So, during the initial phases of the pumping, what we are saying is that the flow is unsteady. That is to say, if you take any radial distance R, all right, for example, you have an observation well, all right, you have a pumping well and then you have an observation well at a distance of R. Okay. You started pumping water from the pumping well, okay, and then you observe what is the drawdown or what is the water surface elevation in the observation well. Initially it will start to go down. So, as a function of time it will be decreasing, all right. So, initially it will be an unsteady process, and that will be true for any radial distance R. Okay. So, if you have many observation wells, in each of them at every R things will be unsteady initially. So, groundwater table will be changing and the drawdowns will also be changing, area of your cone of depression will be increasing, all right, at certain rate. Okay. All right. So, initially the flow will be unsteady, that is to say your both H and S will be function of both R and T. Okay. And other important thing to note is that the pumped water comes out from the storage in the aquifer, unconfined we are talking about. Okay. So, initially when the things are unsteady, all right, where is the water coming from? It is coming from the storage which is there in the aquifer, unconfined aquifer. Okay. And later on we will see that after the things have become steady state or equilibrium state has been reached, right, the groundwater table will go back to the area of influence, and at that point of time you will have the groundwater flow actually taking place from all the directions, all right, all the radial directions. So, the water will be coming out not only from the storage, but also from the flow or the input which is coming from the larger distances. Okay. We will come to that little later. So, this is the first point we want to emphasize, in which we have said that initially things are unsteady as we start to pump the water out. Number 2, with prolonged pumping, if you continue the pumping at the same rate Q, all right, equilibrium state is reached. Equilibrium state is reached. Now, this is important, between the rate of pumping, and the rate of inflow of groundwater, from the edges of your area of influence. Okay. So, what we are saying is that if we continue the pumping with the prolonged pumping, what will happen is equilibrium state will be reached or things will become steady state. That is to say, what do we mean by by saying that the things will be or the flow will be steady state? That is to say, if you make an observation in the observation well, all right, the drawdown will be constant as a function of time. You take any distance r away from the pumping well, your drawdown or the water table will not be going down, all right. You keep on pumping the water, all right, at the same rate, you keep on doing that indefinitely, the water level will remain the same, all right, once the steady state conditions have been reached. In other words, the height of the water table will also remain constant, all right. That is what we mean by that. Why is it happening? It is happening because the reason we have said is this, okay. Let us look at this and then I will come back to this. Why? Because a steady state is reached between the rate of pumping and the rate of inflow of the groundwater from the edges of the area of influence, okay. As we said, during the unsteady case, the water was coming out, or the pumped water was coming out from the storage mainly, okay. But when the steady state conditions are reached, all right, water is coming from storage, or actually it stops coming from the storage, and then it is basically resulting from the groundwater flow, which is coming from the edges of the area of influence, all right. So, if you look at this aquifer or the cone of depression as a control volume, you have some inflow taking place from the farther distances, and then outflow is the Q which is being pumped out, all right, and there is an equilibrium between this output and the input, all right. Same input goes in, same output goes out, storage is same, things are steady state. So, if you think about your Reynolds transport theorem, which we have seen earlier, there is no accumulation. If you have this control volume, there is no accumulation of mass, that is why things are steady state, okay. So, that is number 2. So, at this time, under steady state conditions, we can say that your drawdown will be function of R only, this is S, okay, and your H also will be function of R only. This it will be no longer function of the time, all right, but it will depend upon the radial distance. As you go away, the drawdown will be decreasing and height of the groundwater table will be increasing. The next point, as we pump the water out, is about the cone of depression. The cone of depression will be constant with time. Now, when the things have become steady state, all right. That means the well is operating, or well operates under the steady state conditions. Okay. And these steady state conditions are also called, or also known as, equilibrium conditions. Okay, equilibrium conditions. So, what happens to the cone of depression? Initially, when the things were unsteady, all right, the groundwater table was horizontal, all right, the cone of depression starts to form, all right. Initially, its size is very small, okay. As the pumping is continued, the size or the volume of this cone of depression keeps on increasing. After some time, prolonged pumping, it reaches a constant volume or a constant state. This is called the equilibrium state or equilibrium condition. At that point of time, both S and H become constant, okay. Now, what happens when we stop the pumping? Until now, we said we start the pumping and we keep on continuing the water from the aquifer, all right. As long as we pump the water out, we have reached the steady state conditions, things will be constant, okay. But if we stop the pumping, then what happens? Well, obviously, once you stop the pumping, your output has stopped, but there is inflow taking place, all right. So, the water is flowing in the well, towards the well, because there is a lower energy there, okay. So, what will happen to the cone of depression? Well, the cone of depression will start to reduce, okay, until it will disappear completely and the groundwater table will merge with the original groundwater table, okay. So, let us look at the next point, which is number 4, about what happens when the pumping is stopped. what happens when the pumping is stopped. We just said that one thing that will happen is that the cone of depression will start to or starts to reduce in size, right. That is to say, why is it happening? Because certain observations we want to make, that there is no output from your aquifer well system, right. Our output has stopped, but there is inflow taking place from the edges of the area of influence. Okay. So, inflow is continuously coming into the cone of depression, so that the cone of depression starts to reduce, all right. So, inflow is there, there is no outflow. So, we will have the unsteady conditions. What is the other thing? There will be gradual accumulation of storage as a result of all this, till the groundwater table merges with the original horizontal position. Okay. Okay. Now, this phase, which phase? After we have stopped the pumping, this phase of the activity in the aquifer well system is called recuperation. Okay. It is called the recuperation or recovery. Okay. And I am going to underline these two terms. Okay. This process of changes that are taking place in the aquifer well system after you have stopped the pumping, all right. As we have said that the groundwater table will merge with the original position, right. So, all of this process is called the recuperation or the recovery, all right. Initially, the cone of depression formed due to the pumping. Once it is stopped, it is recovering. The aquifer system is recovering to its original position, all right. So, obviously, it is called the recuperation or recovery. Now, this recuperation process, this will be steady or unsteady? Obviously, it will be unsteady. Okay. As we said, initially the formation of the cone of depression is unsteady process, all right. But if you continue to pump the water, it will remain steady, right. But if you stop the pumping, okay, after let us say 2 days, 3 days or 30 days or whatever, you have pumped the water, and once you stop, then it will be an unsteady process in which recovery of the everything will be taking place. Okay. So, this recovery process is unsteady. Okay. So, if you want to find out the changes in the groundwater table, the drawdowns, etc., during the formation of the cone of depression or initially or during recovery, you will have to use the unsteady flow conditions. The last thing we will say is that the recuperation time, okay, the recuperation time depends on the aquifer characteristics, obviously. Okay. So, what is the recuperation time or recovery time? Basically, the time which is taken by the aquifer well system to come back to its original position, all right, since the pumping has stopped. So, the time elapsed between stoppage of the pumping and full recovery is called the recovery time, all right. This recovery time or the recuperation time will depend upon what? The aquifer characteristics, all right, the transmissibility, the capability of the aquifer to transmit the water or the hydraulic conductivity, all right. So, if you have a highly permeable strata, all right, it will take less time to recuperate, all right, otherwise it will take very long time, all right. The next thing or the last point I would like to make about all this process of pumping, formation of the cone of depression, recovery, all of this. What happens in the case of a confined aquifer? We talked about all those things for an unconfined aquifer. Okay. Let us say you are pumping deep into a confined aquifer, all right. Same thing happens there also. The confined aquifer also undergoes the similar changes. Okay. Everything we have looked at, it happens in the confined aquifer also, except that we do not have a groundwater table in the confined aquifer we saw earlier, right. What do we have? We have what is called the piezometric surface. Okay. All right. So, in a confined aquifer, if you are pumping water from a very deep well which is confined or sandwiched between two rock strata, then what will happen? Exactly the same things will happen. The cone of depression will be formed, all right. Initially things will be unsteady. After a prolonged pumping, things will become steady, all right. Once you stop the pumping, recovery will be taking place, all right. However, the groundwater table is replaced by the piezometric surface. And what is the piezometric surface? Well, if you dig an observation well, all right, the water will rise up to the piezometric point, all right, or the energy whatever is available. Okay. So, if you dig lots of observation wells, you can see that the groundwater or the piezometric surface will form that cone of depression, okay, which will become constant after prolonged pumping, and after you have stopped the pumping, things will start to recuperate back again in the observation wells. Okay. So, exactly the same thing is going to happen. Okay. The last note is about the recovery. In a confined aquifer is very rapid, very quick as compared to, we are saying, the unconfined aquifer. Okay. And why is that? Well, it is because the flow is taking place in a confined aquifer due to the pressure differences. Okay. So, this is about the process of pumping in a well hydraulics. We have seen what happens in the aquifer, all right. This is as far as various definitions is concerned, what is going on inside an aquifer. Now, what we want to do is we want to do some mathematical modeling, so that or we develop some equations, apply Darcy's law and whatever we have learnt, so that we are able to find out how much water can be pumped and what will be the changes in the groundwater table as a function of time and as a function of distance, radial distance r, and so on. Okay. So, we want to analyze all this situation. Okay. So, what we will do is we will take the cases of confined as well as unconfined case. Okay. So, first I am going to take the well hydraulics for the confined case. Okay. Ground water flow towards a well. Okay. So, we are kind of starting a new topic in which we want to model all these things, and within this topic your first case is going to be the steady radial flow, okay, to a well, and we are looking at well is in confined aquifer or case 1, which is your confined case. Okay. So, let us first define everything. Okay. This is your horizontal impervious layer at the bottom, okay, and we are looking at the confined case, and in which this is your ground level. You have a pumping well which completely penetrates the confined aquifer, and this is, let us say, is your confining layer. Okay. Original piezometric surface was, let us say, this much. All right. This is your original piezometric surface. Okay. Under the steady state conditions, let us say it has become like this. All right. So, the thickness of this aquifer is, let us say, B. We will define all the parameters which we are going to be needing, and this is your radius of influence, every distance we are measuring from the center of the pumping valve. Okay. And if you take any two observation wells, okay, let us say this is your S1 and this is your H1. Okay. We are measuring things from the bottom, and this is your R1. So, at any radial distance R1, your height of the piezometric surface is H1 and the drawdown is S1. Okay. And similarly, at any other distance, these things are S2 and H2. Okay. And this is at a distance of R2. Okay. And at any general distance, let us say at any R, these things are H and S. Okay. This is obviously your impermeable strata, the upper one. Okay. This is your piezometric surface during the pumping. During the pumping means what? This is actually your steady state thing, because we are looking at what? Only the steady radial flow. Okay. So, keep that in mind, it is not unsteady. Okay. So, we have defined B, H1, H2 are the other thing is, let us say, the height of your water in the well itself. Let us say this is HW. Okay. This is the height of the water in the well, pumping well, that is HW, and this, let us say, is your SW. Okay. So, the quantity at the well are SW and HW. Okay. All right. So, let me just write down all these things quickly, and then we will go to the derivation. So, B is your aquifer thickness. This is confined case we are looking at. Capital Q is the rate of pumping. Okay. It is the rate of pumping. H is a general height of the piezometric surface. Where at radius R, any general radius R. Okay. And then H1 is what? Is the height of your piezometric surface H at R1. H2 is equal to H at radial distance R2, the way we have defined in the figure, right. Similarly, what is S1? S1 is your drawdown at radial distance R1, S2 is the drawdown at R2, right. Capital H is the height of the piezometric surface. Originally, initially, whatever you want to call it, or you say at R is equal to capital R, which is your radius of influence. Okay. Define 2RW is what? Is the dia or the diameter of your pumping valve. Okay. And you should put it here, that is what we are talking about. This is 2R W, and the water which is pumping out is, let us say, Q. HW is the height of piezometric surface, okay, in the well or at the well, that is R is equal to RW, all right. Okay, let me move on and say SW is the drawdown at the well, R is equal to RW, and Q is the rate of pumping, which is constant, all right. So, these are all the parameters we have defined, okay. Now, what we do is, let us look at what is actually happening in the aquifer if you look at it from the top, okay. So, if you take a cross section in the confined aquifer, all right, cutting the well, all right, and look at from the top how the water is flowing towards the well, okay. What will be the pattern of the flow? Everything is flowing towards the well. Let us say the well is a point in a space, right. So, what you will see is that there is a radial flow taking place from all the direction towards the center of that circle or radius of influence, okay. So, if you see that from the top, what you will have is, if you take any distance r, all right, what you will notice is that the flow is taking place like this towards the well. So, this is what is this is 2r, of course, at any distance r from the pumping well. So, this is, you say, is the radial flow pattern. Okay. Now, what we will do is, we can apply the famous Darcy's law to this radial flow pattern, okay. What will be the radius? Everything is steady, aquifer is homogeneous, isotropic, K is constant in all the directions, right. So, you have, let us say, VR is the radial velocity towards the well, okay, in any direction. That will be equal to what? You have K dH dr, isn't it? As you are going towards the well, this is the velocity which is constant. So, velocity basically occurs across a cylindrical surface, okay. If you are looking from the top, you are actually looking at a cylindrical surface with a cross sectional area of what? Okay. So, if you are looking at it from the side now, this was the top, this is your cylinder. What is its height? This is your aquifer thickness B. Okay. So, what we are looking at is radial flow is taking place towards the well, and then if you are taking the cylinder of the complete depth of your aquifer, the confined aquifer, right, then you are looking at a cylinder, all right, whose length is B and radius is r. This r is, let us say, anything, okay. It may be the radius of influence or any general radial distance r. So, you are looking at a cylinder of radius r and height B, okay. So, if that is your control volume, then velocity or the radial velocity V r is entering into this cylinder, okay. What is the cross sectional area of this radial or this cylindrical element? Well, we can write it down, okay. So, if you did that, this cross sectional area will be equal to what? The circumference is 2 pi r, right, or pi d times B, okay. You can extend this cylinder, and that is what you will find. So, this is the cross sectional area, this is the velocity, all right. How can you find the discharge Q? Discharge Q, which is being pumped out from the pumping well. Well, from the continuity, what is that? It is nothing but velocity into area, isn't it? Q is equal to V A. What is that? This is your VR times 2 pi r b. What is VR? VR is this. So, I am just going to put it here in this equation. So, if you do that, you will have q is equal to what? K dh over dr is the velocity times 2 pi r b. Okay. Now, what you can do is in order to find this q, you can do some algebraic manipulations. All right. We do not know all this quantity. So, we need to do some integration here. So, if you do this, q over 2 pi k b dr over r is equal to dh. All right. What you have done is you have separated the variables h on the right hand side and r on the left hand side. That is all we have done here. Okay. And once we have done that, what you say is you integrate on both sides between two locations. One represents what? h1 comma r1, and 2 represents h2 comma r2. Let me go back and show you what I mean. Okay. Remember, I showed you this r1 h1 and r2 h2. So, what you are doing is basically you are integrating between, let us say this is 1 and this is your 2. Okay. If you do that to this equation, what you will obtain is this: q over 2 pi k b is constant. This will be log of r integrated between r1 and r2, right, which will be r2 over r1. Okay. Integration of 1 times dh is h. So, this will be h2 minus h1. Okay. That means your q is going to be equal to 2 pi k b times h2 minus h1 over natural log of your r2 minus r2 over r1. Okay. This is the expression for your discharge. All right. So, what does it mean? So, you have the observation wells, 2 observation wells at R1 and R2. All you do is you measure the drawdowns or the height of the water table in that. Okay. Once you have that, you can find out what the Q is, and if you know the Q, you can find out any of these things here. Okay. Let me number this equation as 1. This is the famous equation which is known as Thimes equation, THIE Thimes equation. This is also known as equilibrium equation. Why? Because this is derived for the steady state conditions when everything is in equilibrium state. All right. So, let me move on and say that this is, or equation 1 is for the steady radial incompressible flow to a pumping well or towards a pumping well, okay, in a confined aquifer. Keep that in mind, we have considered a confined case. Confined aquifer, what kind of a confined aquifer? Well, which is homogeneous and isotropic. All right. Okay. So, this is what it is, and this equation or Thimes equation is used basically by replacing H with S's. Okay. The equation, if you go back, you see you have the H involved here. So, what is normally done, or normally we say that we actually exploit this condition. What is the total H is equal to S1 plus H1. You go back to the definition sketch. What is your total H? This is your capital H. Okay. What will that be? That will be nothing but your H1 plus S1, and it will also be equal to H2 plus S2. So, instead of H1 and H2, actually we use S1 and S2 in that Thimes equation. All right. So, this would mean your H1 will be equal to what? Capital H minus S1, and similarly your capital H is also equal to S2 plus H2. So, that will give you your H2 as capital H minus S2. Okay. So, you put these things in your equilibrium equation, what you will get is this: Q is equal to 2 pi Kb of your S1 minus S2. Okay. So, earlier we had H2 minus H1, it will be S1 minus S2, and then natural log of R2 over R1. Okay. And this is your equation number 2. Let me put it in a box. Okay. All right. So, now how can you find out this S1 and S2? Well, basically you have the observation wells, and then you find out the distance between the groundwater table and the current groundwater table under steady state conditions. All right. That is your drawdown. Now, further we can use this equation on the boundaries or the boundary conditions. Okay. If you do that at R1 is equal to RW, all right, right at the well. Okay. Right at the well, what do you have S1 as? S1 we have defined as SW, right, and what is H1? And we have said that this is HW. All right. So, the quantities at the well itself are SW and HW. Similarly, what is the other extreme? R2 is equal to, let us say, capital R, the radius of influence. At the radius of influence, what is S2? Can anybody tell me? Well, we have already said that at the radius of influence, the drawdown is 0. So, this is going to be 0, and what will be H2? H2 will be nothing but capital H, right. So, you put these two things in equation 2, you will have a simplified equation which is Q is equal to 2 pi Kb times SW minus 0, right, S1 minus S2, S1 is SW, S2 is 0, divided by natural log of R2 over R1, which is going to be equal to capital R over RW, and then you say that this is also equal to 2 pi T SW, okay, divided by natural log of capital R over RW, all right, where T is equal to K times P, which is the transmissibility of your confined aquifer. Okay. This is your equation number 3. See, the advantage of this equation 3 which we have just derived is what? Is we can find out the aquifer property T. This Q is actually we would know, because we are pumping certain amount of water. So, we know the rate of pumping at the pumping well, right. So, if we want to find out the aquifer properties, right, so then you can get T from this equation. How? Well, all you need to do is you just need to observe the value of drawdown at the well, all right, and you already know the radius at the well, and you also need to know the radius of influence. So, knowing all these things, you can find out the transmissibility of the confined aquifer. Okay. So, transmissibility T of the aquifer can be determined by observing the drawdowns, let us say S1 and S2. I am going to be general here, and we can apply it to the boundary conditions of course, in 2 observation wells, right, which is adjacent to the pumping wells at distances R1 and R2, let us say, okay, from the pumping well. Okay. So that your expression for T then would come out to be Q over 2 pi of your S1 minus S2, this is from equation 2 actually, and then natural log of R2 over R1. Okay. And you can use the well and the radius of influence also, okay, and you can put the things accordingly. Okay. So, this is your equation number 4. So, you see that the case of confined aquifer with steady radial flow towards the well can be used to determine or estimate the aquifer properties. So, once we have the transmissibility by observing the drawdowns into different wells, then we can also find out the hydraulic conductivity if we need to, all right. Or in other words, if we know these drawdowns, we can find out the discharge, and we can do lots of combinations of these things when we have multiple wells, and we can manage the overall groundwater resources. Okay. So, I think I would like to stop at this point of time. So, basically we have started the well hydraulics a topic, the last topic in this course, and we looked at the certain basic definitions, and then we saw the groundwater movement towards the well for a confined case, and what kind of flow it was. We said we are going to look at only the steady case yet, all right. So, in the next class we will look at the unconfined aquifer, and then we will look at the unsteady case. Okay. So, we will stop here today and come back tomorrow. Thank you.